All right, we've talked about velocity, acceleration. Now we're going to look at equations that we need to do to solve typical kinematics problems. And here are our main equations. Just to let you know that this is always when acceleration is constant. That's most thing to understand. If your acceleration changes, obviously we have to do some different things with the numbers. We'll get to that at some point. First equation is right up here, and let's talk about what everything means, okay? A v by itself is velocity final. A v sub naught is initial velocity. All right. So with this first equation, final velocity is equal to initial velocity plus a, hopefully is acceleration, right? And then t is time. So that's this first equation. So final velocity is equal to initial velocity plus acceleration multiplied by time. This next equation, and probably the one I use the most, has x and x sub naught. X is going to be our final position, and x sub naught is going to be our initial position. So our final position is equal to initial position plus initial velocity times t plus 1/2 at squared, acceleration times time squared. And then the rest of these equations will kind of work out, and you can follow what they mean. Now, how do we choose which equation to go with? That's where we have to really be aware of what's going on. Here we got v and o, so this would be when there's no position, right? This equation's best when we don't know the final velocity. This equation's best when we don't know time. Okay? This one doesn't have position, right? Doesn't have position, nor does it even talk about acceleration. This is how to find an average velocity. Okay? This is rarely used. These big three, though, you'll see, plus what I would call the position equation, which is just like this. Okay? That's in a situation as if you don't have an acceleration. But these are all constant acceleration equations. That's why this one's left off the list, but it's still usable. But we will keep this in mind as we look at the problems. So, first problem. You're designing an airport for small planes. One kind of airplane that might use this airfield must reach a speed before takeoff of at least 27.8 meters per second and can accelerate at 2 meters per second squared. If the runway is 150 meters long, can this airplane reach the required speed for takeoff? If not, what minimum length must the runway have? So let's think about everything we know. We know, let's just start writing down. All right, so we got initial velocity. If the airplane's taking off, that is going to be 0. Our final velocity is going to be, or our minimum final velocity is going to be 27.8 meters per second. Our acceleration is going to be 2.0 meters per second squared. I don't see time anywhere when I read this. And then our distance, initial position and final position. Our initial position, since we're starting at the end of the runway, will be 0. And then we're looking at a final position we don't know. So we either got to find time and work our way through or find final position. Since we don't know time and want to find final position, let's look at our equations. Which one does not have time in it, but it has position? Well, it's this one. So I'm going to use this equation to find my distance here. Okay? So I just plug numbers in. I know that my final velocity is 27.8 squared. My initial velocity is going to be 0 squared plus 2 multiplied by my acceleration of 2 times x minus x sub naught, which will be x because it's x minus 0. So I got 27.8 squared equal to 4x. Now I'm not going to work all the way through the math here for you because you can do that in your head. But when I get x, hopefully I get 193 meters. Okay? So when I look at this runway design, The runway is 150 meters long. Can this airplane reach required speed for takeoff? No. The runway has to be at least 193, but if we put it in terms of 10, I think if we could say a 200-meter runway would probably be the perfect thing for us in this situation. Okay, so there's a problem. Now let's talk about problem solving and what I did here. The first steps, I mean, always read the problem, obviously, but even give it a reread just to be sure that you're reading everything properly, especially if there's a lot of words or if it's really long. Decide what we're talking about here, okay, and what we know, and that's probably the most important thing. What do we know about that object? You know, in this case, we're talking about a runway in the airplane. So the airplane, what do we know about the airplane? Well, we know different things about it. Draw a picture. I didn't draw a picture there. I'll draw one with the rest of these examples, but drawing a picture always helps. Especially if you take the AP test and draw pictures, you might get points for it. List your knowns and unknowns. With kinematics, it's pretty easy. You just start to list down all the velocities and distances and accelerations and times and all of that. At some point, though, you'll figure out what you're missing. Then consider the physics you're using. In this case, we're using kinematics because we know that, but as we move on, we're going to have energy, we're going to have momentum, we're going to have all these different things coming in there. And then we look at the equations that we can use. Once we pick our equation, we solve to get an answer, and then we see if the answer makes sense. Units and sig figs come at the end, but probably the most important thing is to make sure it makes sense. These will take care of themselves. Most of you are pretty adept at that. But those are the steps we want to go through. Not every problem requires you to do this, but it's always something to fall back on if you're stuck on a problem. So here's another example. How long does it take a car to cross a 30.0 meter wide intersection after the light turns green if the car accelerates from rest at a constant 2 meters per second squared? So we got a little car, and we got a green light. That light turns green, right? That car takes off, okay? So we're going to make everything going positive. Our acceleration is going to be positive. That means our velocity is going to be positive and so forth, okay? So what do we know? Well, let's write down. Do we know our initial velocity? Sure do, because we are at rest. All right, where does it say right here? From rest, we're going to be at 0 meters per second. Final velocity, not sure. We can probably figure it out, though, if we need to. Acceleration, we know the car accelerates 2 meters per second squared. Time, we don't know. Position, well, we know our starting position is going to be 0. This is going to be our origin there, so we'll be at 0. But then our final position, we want to see how long it takes us to get to 30 meters. So we're going to say that's going to be our final position. So we know position, we know initial velocity, we know acceleration, we don't know final velocity, we don't know time. So which equation does not have final velocity, but it has time? This one right here. Then once we figure that out, what equation we want to use, let's just pop the numbers in and go. So x is 30. X sub naught is 0. Our initial velocity is 0. So we're going to multiply that by t. That'll be easy. Plus 1/2 a, which is 2, times t squared. We'll get rid of all these zeros, and 30 is going to be equal to 1/2 2 times t squared. And again, I'm not going to insult you by doing this math for you, okay? But when we do this in the end, and we'll get a square root, t should equal 5.48 seconds. So this car will take 5.48 seconds to get to where it has to go. Here's another example, airbags. Suppose we want to design an airbag system that could protect a driver in a head-on collision at a speed of 100 kilometers per hour or 60 miles per hour. Estimate how fast the airbag must inflate to effectively protect a driver. How does the use of the seatbelt help the driver? You know, that's an interesting question about the seatbelt, but we're not going to worry about that right now. Let's see what we know. Okay, based on everything we read here, we must first look at the speed, and we got the speed to be 100 kilometers per hour. Let's convert that to meters per second here. Okay, we know there's 1,000 kilometers in a meter. And we know in 1 hour it's 3,600 seconds. So I work my way through this, and I get my speed to be 28 meters per second. So that's going to be the initial velocity there. Now, once I know initial velocity, what else do I have to know? Well, we look at this this airbag system and the deployment of the airbag. We know with the airbag in the wreck that the distance traveled, we'll guess approximately, and again, we're not given the information, but we'll make a guess. We'll say our final position will be 1 meter of crumpling that will occur. Sometimes you have to make some of these assessment or estimates when you're solving problems. So about 1 meter, and once we know that, we know our final velocity, because we're stopping, is going to be 0. We know our initial velocity is 28 meters per second, and we know our distances. So with that, we can find acceleration, because we don't have to worry about time, because we're looking right here at this equation. Okay, so now it's all plug and go. So our final velocity is 0. Our initial velocity is 28 squared plus 2a times 1, right? Because we're gonna crumple up at 1. So we're gonna use some algebra here. We're gonna go minus 2a is equal to 28 squared. Okay, and our acceleration is going to end up being negative. And when we do the math, we're going to get negative 390 meters per second squared. So that's the acceleration for that to happen. Now, once we know that, let's see what our time frame is for this. Okay, so we know acceleration, and we know our initial, wrong button there, we know our final, and we know our initial and final velocities. So now we can go to this equation. Final velocity is 28. Okay, our initial velocity is 0, plus our acceleration of negative 390 multiplied by t. And t, as you can guess, is going to be a really small number. When we do the algebra to solve for t, we get 0.07 seconds. So that's how much time we have to get there. Interesting, isn't it? Let's look at one more situation about reaction time and braking distance. And I kind of put it out here so we could see the numbers, but we just want to figure out which equation to use. So we got a constant 14 meters per second at this time with this acceleration. Okay, so for reaction time, it's the time we know the stop's coming. It takes 0.5 of a second for us to hit the brakes. After we hit the brakes, then we're going to have to slow this sucker down. Okay, and so what we're looking for is see how much distance we're going to travel here. So right here, let's see how much distance we're going to travel in this portion of our problem. We know our velocity. Okay, is going to be constant. Okay, we know our time's 0.5 seconds, and we know our acceleration is going to be 0. All right, so what we're looking for is distance with time in a constant velocity. So I mean, we can go right here with this one and make it really easy. So x sub naught is going to be where we start, so that'll be 0, plus our velocity of 14 times 0.5 plus 1/2, our acceleration 0, so that eliminates this completely. X is going to be 14 times 0.5, which is going to be 7 meters. So this distance is 7 meters. So we go 7 meters before we hit the brakes. Now we want to see what happens during braking. So our distance x is going to be x sub naught, right, which is 0, plus our velocity 14 times our time frame, which we don't know. So we can't use this equation, can we? So we have to think about an equation that doesn't have time. So we go here. V squared, which is our final velocity, which will be 0, is equal to v squared 14 squared plus 2 times negative 6 times x. And we want to solve this for x, and when we solve for x, we get 16 meters